We're in the middle of investigating the current proof of work system in the application and ways to improvement. The system in place checks for leading zero characters of the hexadecimal hash. But Bitcoin uses a leading zero bits check on binary hashes, which offers a more fine-grained difficulty adjustment. So let's refactor our approach to follow the same binary hash strategy. So head back to the command line and let's install a library called hex2binary, which can convert a string number in hexadecimal form to a string equivalent of its binary form. So let's install this library called hex2binary. Notice that it has dashes hex-2-binary, and the version used in this course is 1.0.1, and go ahead and add the save flag since this is going to be a dependency for the project. And now head back to the code itself. In the crypto hash function, we can use this new module to return the binary form of the hash string. So in cryptohash.js, right at the top, we can import the hex2binary function from the new module. So let's camel case hex2binary for the exported function. And as a result, we'll require the hex2binary module. So that's all with dashes. So this export of hex2binary is the actual function. So what we can do is we can wrap the return value of the crypto hash function with a call to that function itself. So instead of returning only hash.digest hex, we'll make sure to convert the overall hash.digest of hex with a call to hex2binary so that we get the binary equivalent. And now all the hashes will actually return in a binary form. So with this change, let's see the effects on the average work script. So let's see if we actually get different difficulties when we run node averagework.js. And immediately you'll find that the difficulty rises to about 17. So clearly something has changed. And once again, I'm going to use some movie magic to jump ahead around 3 minutes or so when the average time has had a chance to converge around a specific value. All right, welcome back. And if you've waited for a while, you'll find that the average difficulty is a much more satisfying average time, as it's very close to that mine rate of 1,000 milliseconds. Great. So this seems awesome. We have a hex2binary implementation, which allows us to check for leading zero bits of the binary version of the hash, making it so that our difficulty adjustment is much more fine-grained, and therefore it's close to hitting that 1,000 millisecond value of the set mine rate. Now, there is one downside of our current placement of the hex2binary conversion, is that now our hashes are huge strings of 256 0 and 1 binary bits. So to demonstrate this, let's go ahead and kill this script. And right in our average work.js file, let's add a console.log of that first newly added block. So for now, let's comment out the current logs of the time to mine block, and instead, right after blockchain.add block, we'll console.log that this is the first block, and we'll log whatever is at blockchain.chain, and then we'll find whatever is the last block with blockchain.chain.length -1. All right, so that'll give us the most recent block in the chain, which should have an actual hash in the binary form. As we save this, let's go ahead and rerun the script. And then immediately you'll find that this hash is, it's huge. The hexadecimal form was much more digestible before. So what we can do is we can place the hex2binary conversion somewhere else. Rather than converting all hashes to their binary form, let's only convert it when we're doing the difficulty check. So let's take out the hex2binary function from the CryptoHash implementation. So even though it's nice to have it here, we're going to remove it for the sake of maintaining hexadecimal hashes when we want to print the block value. And then we can do the conversion in the mineBlock function of the block.js file. So let's require hex2binary at the top of the block.js file. So const hex2binary is the result of requiring the hex2binary module. And let's actually place this as the top export since it's grabbing from the node module's location rather than the local files. And then right where we're creating the difficulty check, we're going to convert the hash to the hex to binary form first. So let's wrap the hex to binary, or rather let's wrap the hash in a call to the hex to binary function. And now this will make it so that we're still doing a difficulty check based off the binary version of the hash. So as we do this, back in the averagework.js file, let's comment back in our code for the time to mine the block. And we should still see that very fine-grained difficulty adjustment. So once you have that change in, go ahead and run the script one more time. And then you'll see that the hash is still a nicely readable hexadecimal version of the hash, but you'll find that the difficulty gets very fine-grained and goes all the way up to the high values of 18 to 20, as we saw before with the binary bits value version for this difficulty adjustment check. Cool. So this means that our average time to add a new block will eventually converge to a value near our mine rate once more. All right, nice. So we now have a superior proof of work system based on binary hashes. Last up, since we did some refactoring, we need to make sure that the test suite is just fine and we haven't broken anything. So make sure to run npm run test. And what you'll find is that we actually have one failing test now. And that's because there's a difference between our test, which is checking based off the hexadecimal form, but in our code, we had the hex to binary code converting the hash to the binary form in order to check the difficulty criteria. So we need to adjust that within the block.test.js file as well. At the top, import the hex to binary function, and then this is the result of requiring from the hex to binary module. Cool. And in the place where we're checking that the hash matches, so right here where it says it sets a hash that matches the difficulty criteria, well, we also need to check it based off the hex to binary version of that overall hash. And as we save this, once the mine_block.hash is wrapped, you'll find that the test suite is green once more. All right, awesome. So with that change, we have a fully passing test suite, and we have now a superior version of the proof of work system that is based on the binary hashes of the block. All right, that's pretty awesome, but there's still ways that we need to improve this difficulty adjustment system. So head to the mine_block function of the block.js file. One thing you'll notice is that the difficulty adjusts every single time in the block. So at every iteration, the difficulty is adjusting. This begs the question, could an attacker expose this system? And the answer is yes. Currently, there is nothing stopping an attacker from arbitrarily choosing an extremely low difficulty for the next block, and then generating a valid hash from the last block's hash and whatever data that they want with their own low difficulty. However, now since we've anticipated the attack, let's add the shields through some protection code to make sure that our blockchain system is not vulnerable to this attack next.